Great. So let's get started. So thank you everyone for coming, both here in Utah and also online. Today we're hosting the Cosmic AI seminar at the University of Utah, and so I'm very pleased to have as speakers Kyle Dawson and Tyler Hagen from the Department of Physics and Astronomy here in Utah. Kyle's an old friend, and we've been working for a long time to try and build interactions between astronomy and CS, and so this is continuing in this series. He's a professor here. He did his postdoc at Lawrence Berkeley National Lab, since has been involved in a number of major spectroscopic studies, so BOSS, eBOSS, and now DESI, which he'll be telling us about. And then Tyler Hagen is a Ph.D. candidate in the physics and astronomy. Will tell us about some work looking at the data to kind of how applying machine learning AI can help lead to some scientific discoveries. So at this point, I'll hand over to Kyle. So thank you.
Great. Thanks, Jeff. Thanks, everybody, for joining. As Jeff mentioned, I'm going to talk about specifically the Dark Energy Spectroscopic Instrument and our 3-year results. Before I do so, let me just, Before I do so, let me just remind everybody that this is a very large collaboration. I actually see several collaboration members online on Zoom, which is great. Our collaboration has about 1,000 members across the globe, something like 72 institutions. And over the last, I've been working on this for about 13 years, since we started the first design phase. And it's been a really wonderful experience with all my colleagues, and I'm very proud of the work we've done. Okay, so this will be a talk where I present the first half, and what I'm going to do is give the very high-level overview of the Dark Energy Spectroscopic Instrument and some of our cosmology goals and results. That will then segue to the second part of the talk, where we talk about some of the challenges in extracting more information from our data than what the biggest results have been. There's a lot more at play than what we've gotten a lot of our press for. And Tyler's going to talk about some of those challenges, and he's going to compare what happens when we use machine learning techniques to try to address the challenges versus other more physically motivated techniques where we kind of really understand what's happening at all the steps of the analysis. And he's going to do, talk about a little bit both, but mostly about what are the consequences and a little bit like who wins, okay? Okay, so first, this is a project to study cosmology, and more specifically, dark energy. Dark energy is a major component of today's universe. It makes up about 70% of the energy density, and has very peculiar behavior that was first revealed by observations of Type 1a supernova back in the 90s. Type 1a supernova have a luminosity when they explode that's fairly well understood. So it gives you a way of addressing one of the biggest challenges in astronomy. How do I measure distances? And it really works basically through the inverse square law. You measure its distance by its apparent brightness. If you know its luminosity, the distance goes as 1r squared. The flux goes as 1r squared. So with these relative distance measurements, back in the 90s, we measure the expansion history of the universe by measuring effectively what's the distance to different epochs in cosmic history. Basically, how much has the universe expanded to different epochs back in the time. So on the x-axis here is redshift. On the y-axis is a proxy for distance. And as you can imagine, as I go further out in redshift, which is the factor by which the universe has expanded, what is the distance to those objects? And what they found using roughly 50 supernova was that as you went further away, or you went to higher redshift, the supernova actually were more distant than one would expect if you had a universe made completely out of matter. So the expansion equation that drives the universe, this Hubble law right here, h squared of a equals blah, 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 had other components in the energy density that were beyond the standard model for physics. So there's the big surprise. It led to the 2011 Nobel Prize in Physics. And what that extra component is actually makes up about 70% of the current energy density in the universe. And it causes a behavior that's very different from what you usually see when matter couples to gravity. It causes a behavior that causes the universe to accelerate in its expansion rather than decelerate. This preference for dark energy, specifically this lambda component, was at about the 3 to 4 sigma level. That was sufficient back then for other reasons to lead the Nobel Prize. It was a huge discovery. I would actually say this is one of the, I actually probably say one of the 5 basic discoveries in the last 100 years in physics. The standard model that arose from the late 90s when we discovered the accelerating universe was that this component would be described as the cosmological constant. It is effectively an energy component that has a density that does not change with time. So as the universe expands, everything else that you normally think of, the energy density would dilute because it's fixed number of particles in a larger volume. So the E equals mc squared term is fixed, but the volume changes and you get a decrease in energy density. This dark energy, described by the cosmological constant, it's flat. The energy density is constant over all time, even as the universe expands. Okay? Usually when I give this talk, I like to focus on how different methods of analyzing the supernova led to different levels of significance, ranging between 3 and 4 sigma, ruling out the previous model of a mega matter-only universe. I won't go into that much today, but this actually is kind of this trend that it kind of gives you a highlight of how much we understand the supernova samples. There's some uncertainty in how those are dealt with in analysis. Okay, so complementing supernova as a technique that we developed is for industrial use in cosmology back in the eBOSS project, starting in 2009. It's called the Baryon acoustic oscillation technique, and it's a different way of measuring the distance redshift relationship beyond what supernova do. Whereas supernova offer you a luminosity that you can then use to make relative distance measurements by how bright it appears through the inverse square law. The Baryon acoustic oscillation feature offers a fixed geometric scale that you can then use by basically just measuring angles, right? It's just like doing a survey. You measure the angle as a function of redshift, and that gives you the distance to the probe. These features originate very early in the universe, something like 10 to the minus 32 seconds after the Big Bang. At that point, this early inflationary field collapses and leaves a very widely distributed, mostly uniform distribution of matter, but it's not perfectly uniform because of quantum mechanical processes. And all the fluctuations in that initial fluid, they propagate outward. The information propagates outward at the sound speed. And it does so for about 300,000 years. At 300,000 years, the state of the universe changes, and these waves get frozen in time for all the rest of the universe's history, okay? Starting from the time of the cosmic background formation up until today. So you now have this preferred feature from these sound waves that's embedded everywhere in the matter distribution in the universe. And wherever there's matter, there are galaxies. Galaxies preferentially form in overdense regions. So here in this cartoon version of the universe today, you see galaxies forming along with this preferred feature. Okay, this preferred feature gives us a preferred separation between 2 galaxies of about 500 million light years. That's actually the unit on the x-axis here. Okay, we're using a different unit, but this peak right here tells me there's an excess probability of finding 2 galaxies with a separation of 500 million light years compared to 400 million or 600 million. Okay, and that's there for all redshifts, all different types of matter. What you have to do is make your measurements of galaxies, measure your correlation function, and look for this preferred feature. Okay. The goal now in combining all my supernova measurements that I've had since the 90s, plus Baryon acoustic oscillation measurements that we've developed, plus measurements from the cosmic background, is to dig deeper into that equation of state for dark energy. Basically it's a null question. Is this dark energy something that has a constant energy density at all of time. If it does, it gives a very particular behavior in the distance redshift relationship. Here are two different measurements of distance versus redshift. And the null hypothesis would be that these distances normalized by my prediction from that cosmological model are just one everywhere, okay? Here and here. At this level of what we understand, we're kind of exploring things at the sub% level and deviating from this prediction. We've already ruled out everything that's outside these contours. So now the next generation experiment, we need to be able to look for things at this level of discrepancy from the prediction. So multiple measurements, all at sub% precision. And it has to be over multiple redshifts. So different probes have different sensitivities. You can see there's a lot of information here at the lowest redshift, less so around here, and then more so over here in this particular distance measure. And then you can make similar arguments for this particular distance measure. Okay, so that's the challenge. We developed, as a follow-up to the Sloan-Digital Sky Survey experiment, where we had an extragalactic survey, specifically focusing on the cosmology. Sloan now moves on to other physics, whereas we took the cosmology component out and put it on a new instrument called the Dark Energy Spectroscopic Instrument. We took over the 4-meter Mayall telescope in Arizona, and we also instrumented it with our own spectrograph system. This spectrograph system is quite a bit more powerful than we had in the past, plus it's a larger mirror. So it gives you something like 10 to 20 times faster survey speed than what we had in Sloan. We designed our experiment, which actually Tyler will explain more than I will, actually. But we designed the experiment specifically around making these Baryon oscillation measurements at a very high precision, which really means you have to choose objects to observe over a wide redshift range and a high number density, and you got to balance your everything to get your optimal BAO measurements. In terms of the instrument is a spectrograph that sits in the spectrograph sits in a nice temperature-controlled closet, and it's fed by a fiber positioner system that's at the prime focus of the telescope. In that prime focused system, I have 5,000 robots, each with 2 degrees of freedom, where I align the position of a fiber optic to the location of an object that's selected from imaging data, from which I can then take a spectrum. And I can take 5,000 spectra at a time. I run them through my 10 spectrographs. And the main thing we're trying to deduce from each of those is the redshift. Basically, what's the proxy for its distance? And then we're going to measure that redshift versus distance relationship through the BAO feature. Okay. At this point in time, we've already created, actually after 1 year, we'd already created the biggest galaxy redshift survey in astronomy. We're now quite a bit bigger than we were after the first year. We've completed results and analysis from a 3-year sample. And the survey covers the lowest redshift with a certain type of target class we call the bright galaxy survey, all the way out as I go to increasing redshift or increasing distance with different probes and I choose my probe depending on what I can identify in imaging data and what I can get a redshift for. And that is a carefully tuned sample based on the performance of the instrument that we characterized back in 2020. Okay. At the end of the day, we're probably going to have something like 65 million extragalactic redshifts. We've actually we've gone at a faster rate than expected, and we think we're going to observe for longer than originally planned because so far the results have been very, very good. Okay. What Tyler will talk about is one particular sample, the emission line galaxy sample. This actually is the most challenging for us to understand, which is why we've developed all these techniques to understand the clustering in that galaxy sample. And the reason it's challenging is because it's sampling a redshift range or a distance that's as far out as we can go with galaxies. Okay, this is quasars, that's a different type of tracer. But galaxies, we go as far out as possible, which makes them very faint. It also has features that are hard to identify, and that's created some challenges in our interpretation of the data. Not for the Baryon acoustic oscillation feature, but for other measurements. Okay, so here is what our three-dimensional map looks like, right? We get the galaxy redshifts, we have their angular positions from imaging, we get the third coordinate from redshift, we make a 3D map, and in this 3D map, we just count pairs of galaxies and count the probability as a function of separation relative to a random distribution. It's a little kludgy with the zoom, but it's a beautiful map where you can see at lowest redshift, you can really see the resolved structure of that like sponge-like topography that we're all very familiar with from numerical simulations. There you have enough number density to really tease out that structure. As I go to higher and higher redshift, things are harder to find, but there's still a lot of information out there as well. The other thing is you go to higher redshift, there's been less time for that structure to form, so it's not quite as pronounced. Okay.
Was the resolution fuzzier out there as well?
No, it shouldn't be. There's some games with like the way we turn redshift into distance here, so it's not quite the scale, and that might be what's making it look like that. Try this trick. Okay. So we have our 3D map. From our map, we can go into different redshift intervals, starting with the lowest redshift interval with what we call the BGS sample, and going from left to right, I go to increasing redshift, and I can tease out in each of those bins that very particular feature, which you see clearly at very high significance. I model it, and the aggregate precision over all of these measurements turns out to be about 0.28%, which puts us in the regime of really testing the models, or really putting putting pressure on that model for lambda CDM that we've been assuming was the case for cosmology for the last 25 years, okay? So from these, we do our modeling. I'm going to present the cosmological results. What I'm going to present from are our two primary papers that have come out of the collaboration so far. The first was in 2024, and that was from the analysis from our first-year sample. The second is from our 3-year sample that came out in 2025. And this had major coverage. We were very excited to see the results. One of the examples of some press coverage was here from the New York Times, where the science writer, stepped out of retirement to come back and write this article because it was, such a surprise, and it's something we've been looking for 25 years, was testing lambda CM at this level. Okay, so I'm not going to spend that much time, but here's the bottom line result: is we bring in this model as a null test on lambda CDM, where instead of allowing lambda to be something that's a constant energy over all time, we allow it to evolve in a linear way. And we have two parameters that describe the linear evolution. One is going to be W naught, which corresponds to, basically gives you what's the energy density today, what's the equation of state for today. And the second is WA, which allows this equation of state to vary with time. So anything that differs from the horizontal line tells you that it's not a constant, that it actually is something that's evolving with time. And the prediction from Einstein's theory of relativity, where it's the standard cosmological constant, that's been the presumed model, is where these two dashed lines intersect. So that was the model that was assumed for 25 years. Here are 3 different manifestations of our measurement, combining our measurement with the CMB data and each of 3 different supernova samples. And this is kind of getting that same thing I teased at earlier, is there's some degree of uncertainty in the way the supernova modeling is handled. People handle basically the correction to luminosities a little bit differently, selection effects a little bit differently, and that causes these contours to wiggle. These measurements are actually fairly highly correlated, especially the blue and the orange are very highly correlated in terms of data sample. But in any case, they all differ from the standard prediction by more than 2 sigma. And the level varies from the weakest tension, which I would actually put into the mundane category of 2.8 sigma. Something like half of 3 sigma measurements in cosmology or in astronomy turn out to not turn out to be anything interesting. So I'd say this is in the mundane category, and it's very rare you get things at the 4.2 sigma level where it's not real. Okay, so super exciting. People like to focus on this particular result because it produces the highest tension with the standard model. But I don't actually, it's very hard for me to disentangle all the different aspects of the supernova studies to say why one would be right and the other would be wrong. So what we present is we put them all on equal footing, and then we leave it to the reader to decide, and we also leave it to the supernova community to help to figure out how to get more cohesion between their 3 different analysis techniques. Okay. Giving a little intuition for where the signal comes from. Okay, if I were to model the DESI data only, here are our DESI measurements in that same Hubble diagram. It's now normalized by my lambda CDM model, where that's the dashed line that's equal to 1. We actually have tension with that model by ourselves. Okay. But we're able to describe that tension by just turning other knobs in the standard model without introducing any new flavor to dark energy. And that's the blue model. That's this blue curve, okay? But our measurements don't have that higher precision down at the lowest redshift range, right? Our last good measurement is right here. And remember from the earlier plots, a lot of the sensitivity was over here. That's where you really want to be driving it. You want to be able to contrast this area with this area to really make a sensitive measurement. So we get super sensitive over in this area. And you see that when you introduce the supernova in this black data points, they line up pretty well with our measurements where they overlap. But then they exhibit a behavior at low redshift that's impossible to incorporate into this lambda CDM model. So you can't twist that blue curve with any different parameterization to pass through these data points and these data points. You can't get that inflection. The only way to get that inflection is to change the time evolving behavior of dark energy. And that's where this 4 sigma tension comes from. This particular sample is the one that gets the 4.2 sigma preference for a time evolving equation, say, for dark energy. Okay? So
what's happening at 0.5 redshift?
This one right here?
Yeah, okay.
Yep.
And at 1.5, those 2 data points seem really
off. Okay, so if I look at the blue curve or the red dash curve, let's just first of all look at a model comparison. For our data points, which are these colored ones, the 2 models were almost indistinguishable in that redshift range, right? You can't tell this from this. Then you ask, okay, how do the data compare to the model? You can calculate a chi-squared statistic. It looks great, but you can also do your chi by eye. These are all completely independent measurements. There's no covariance between them. And 1, 2, 3, 4, 5, 6 of them go through the model and 1 doesn't, which is what you would typically expect.
just random.
I think it's just a random fluctuation, exactly. But yeah, I mean, you expect 1 out of every 3 to not overlap with the model within the contours, and 1 out of 6 doesn't. So it looks totally normal to me. Yeah.
It's really off.
Well, it's off by 2 sigma. Yeah, it happens. But the chi-square, the quality of the fit, everything looks really nice in this, actually. And also, this is not the entirety of the data sample. I'm only showing 1 parameter. We also make that other measurement, the DA, or there's other ways to reflect it. And then you see the overall fit is even better. So it's just this particular, the chance of this particular visualization. Okay. Okay. So now, I usually when I give this talk, I focus entirely on how robust these measurements are. I talk a lot about more of the cosmological model, but I want to move to the next part of our analysis, which is that there's actually a lot more information in the clustering of these galaxies than what I presented. I've shown you the easiest part. The easiest part is to look for this very specific feature that appears only around 500 million light years. And it's really, really hard to create a spurious signal that looks like that. You can't have things in the galaxy that do that. You can't have problems in your instrument. It's very, 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 very hard to corrupt that signal. And we've done all kinds of tests. and it just looks totally robust against every test we've even performed, even tests that I thought we would fail. Okay? However, if anyone's seen a power spectrum from the CMB, you see there's a lot more information than just looking at one feature. There's the slope, there's changes in the slope, there's wiggles. We have the same thing in the clustering of galaxies. We actually have an advantage over the CMB in that we can do that clustering in 3 dimensions. And here is my correlation function for each of my different tracers. This is actually from eBOSS, the project before DESI, where you can see signal in both the transverse direction, the transversal line of sight, and radial direction, parallel line of sight. And it's smoothly varying. You can clearly see one particular thing is the BAO feature, but you see other smooth signal in here. And that has a lot of additional information in cosmology for the matter density, for growth of structure, for neutrino masses, for the effective number of species. There's tons of information. It's a lot harder to extract because it's now smoothly varying. And you can create problems in your data sample that give you smoothly varying effects that are easily to marginalize out for BAO, but not for these measurements. Okay? One example of a cosmological parameter we measure this is the amplitude of the structure, basically, how much structure is formed since the time the universe began. And we get really clean measurements with different realizations of the data and different models. So this is an example of the type of physics we want to extract beyond BAO. Okay? So I'm going to wrap up. I'm going to turn the floor over to Tyler. Before I do so, let me just remind you that DESI is the largest spectroscopic galaxy survey that's ever been conducted. We're seeing interesting tensions with the standard model, which are hints of new physics. I don't know yet how to interpret the difference in 3 different supernova samples or the level of the tension, but it's super exciting, much more than I thought it would be when I started the project. And as we get into the tolerance part of the talk, let me just remind you, there's a lot more physics accessible, but the correct cosmological inference is more challenging as observational artifacts can contaminate the broadband clustering signal. Okay, and that's the source of the talk, the title of our talk. So I can take questions as we turn the floor over to Tyler. Anyone want to, it's kind of like this is a natural breaking point.
Yeah, so if there are any questions online, you can post them in the chat.
Any questions in here? Is the Earth at the center of the DESI map? The way we present it from the observer frame, so yes. So even though the Earth is not at the center of the universe, even though we would like it all to be, the Earth is at the center of the map, yes. So what that map looks like is the distribution of galaxies and a radial separation from our frame. Do you correct for multiple testing when you compare different models? Correct for multiple testing. So multiple testing comes in a couple of flavors, so I'm not quite sure how to answer that. The one thing we do is to test the robustness of the data is we test it all in a model agnostic way, only internal to DESI. So that's of no consequence to the cosmological model or the other data sets. That's the primary test that we do. So when I say we pass the robustness test, I basically ask the question, for one redshift in one sample, can I change the configuration of my experiment and change the result? And the answer has always been no. So it's a completely model independent test that we've conducted. And that's the primary thing that we've evaluated. So I hope that answers the question. It's when I say testing, it's very much on the experimental side rather than like the modeling or inference side. Okay.
Great. Neil will hand over to.
Ready?
So Tyler.
You correct it all for, do you have any estimates of the curvature of the universe or you assume it?
Okay, so there's tons of cosmology I've ignored in here, one of which is curvature. There's actually interesting things in the matter density and neutrino mass. For sake of time, I didn't do any of that, but yes, we absolutely test for curvature. And whatever parameterization we use for our cosmological model, we don't find a preference for curvature away from 0.
the curvature will not, evolution of curvature does not account for the tension.
I mean, there's papers, with the supernova, it's very hard to describe with curvature.
Okay.
Let me say it that way. You can describe some of the tension just between CMB and DESI by changing the curvature, but it's actually pretty hard to do as well. Okay. Yeah. So, but yeah, I mean, the best way to do it, to have with the supernova, that inflection, that you have to have something more complicated at changing the equation state.
There's one more question on Zoom.
So what do you think, what do you think is the main systematic or observational artifact that could contaminate the signal?
Okay, so from the BAO, every test we've done, the level of systematic errors is at the level of 0.1 to 0.15%. And my personal opinion is we're being way too conservative on that, and it's actually better than that. The systematic errors don't come from the data, they come from how we do the modeling, or possibly what we assume in our cosmological inference from the beginning. But there's some coupling between things, and it is a very, very small error. It's very, very hard to find anything in the data that causes a systematic error. Like I said, we've done some extremely strange tests, and it's passed them with flying colors, where I wouldn't think it would pass. So the bigger question is now to the next part of our talk, where when we actually look for smoothly varying signal, there are systematics in the data that will cause problems. And what they'll do is they'll change not like the peak of the BAO, but they'll change the slope or the general structure of the correlation function in ways that are non-physical and can be confused with cosmology. And that's what Tyler is going to get more into.
Great transition, so it's great. So Tyler, take it away.
Yeah, okay. Great. Thanks, Kyle, for that awesome description of DESI and really the power of these modern spectroscopic galaxy surveys and all the wonderful things we can learn about the universe and dark energy. So as Jeff had mentioned, my name is Tyler. I'm a grad student here at Utah in the Department of Physics and Astronomy. And for several years now, I've been working with Kyle and been a member of DESI for my PhD research. And today I'm going to talk about a subtle but important step in the DESI pipeline in which they employ some machine learning, a neural network. So before I get into those details, I want to sort of start at the fundamental level. So all of the beautiful constraints that have already been shown today really rely on DESI's ability to measure the spectrum of a galaxy, okay, from which we get the redshift and the distance, and we create this great 3D map. But DESI does not just blindly measure the spectra of things in the sky, right? It's an informed decision. So how exactly does DESI decide which galaxies to follow up with spectroscopic measurement? So the answer here is imaging, okay, or in astronomy, what we call photometry. So this is an image taken directly from the DESI legacy imaging surveys, where we effectively take pictures of the sky in different filters or different colors, and from which we can identify the targets of interest for DESI spectroscopic survey. So, you can see many galaxies here. It's not, the wonderful resolution that you see with the Hubble Space Telescope, because we're ground-based here. But you see some extended edge-on galaxies. All of these small points can also be targets for DESI. And it is through this imaging data that we choose which ones to follow up, put a fiber on the size of my hair, and collect the light for spectroscopy. So the answer to the question is imaging. So I want to explain a little bit the relationship between the imaging and the spectroscopy. So, this is ultimately a beautiful redshift of a nearby large galaxy that's conveniently being blocked by the conference room window, but it's great. And so you can see, some broadband continuum flux here in the spectrum coming from the underlying stars in the galaxy. You see these absorption features coming from cold gas eating away specific energies. You see emission lines coming from excited gas emitting at certain energies. And it's through those features that we can really get the redshift and the distance to these galaxies. Okay? But before we get this beautifully resolved spectrum, we go through the imaging, which is effectively the integrated light in the spectrum through several different filters. Okay, so these are 3 different filters that DESI uses, known as the G, R, and Z. And so you can imagine by integrating the light in these filters through our imaging, I effectively get 3 data points. Okay, and it's through these data points that I can calculate the differences and get some sort of intuition on the colors and the brightnesses of these galaxies to make an informed decision on what I measure spectroscopically afterwards. So, this is really the foundation of targeting for DESI. And the real advantage of this photometry is it enables an efficient and field-level survey where we can just run an algorithm on the whole image and find all the possible sources for spectroscopic follow-up.
Please, stupid question.
Yes,
There are a
of
lot
course.
things that call spectrum, light spectrum of the different elements. So where is the zero redshift hydrogen wavelength?
That's it's like 5,600 angstroms or so. You get multiple different lines depending on the energy gaps.
The first
Go ahead.
transition is at 6,500.
65, right.
Angstroms.
Okay,
That's the 2 to 3 transition.
okay.
And then we have transitions throughout. And I think what we were seeing on the previous slide was a combination of oxygen and hydrogen in the
Okay, that's right. So these are all peaks are related to oxygen hydrogen transition.
That's the most typical, would be
Okay.
those two.
Okay.
Yeah, that looks to be like both. I see some oxygen for sure. And then this is redshifted. So this is not very
Yes.
high redshift.
I mean, you might, for
This
this
is like
audience,
1 or something.
you know, you guys have been mentioning redshift and all. You might want to just talk about basic hydrogen absorption or emission redshift measurement.
Yeah, we model, this is the data that goes to the spectrograph, and then we have a model that predicts where the hydrogen and oxygen emission will be in absorption
And then
and the
we-
broad features.
Right.
And then the 3 parameter in that model is basically the property of the stellar population and then the redshift.
Okay.
So this right here is, I can see by eye, this is from calcium. This is at 3,933 angstroms. This is 3,967 angstroms in the rest frame. So then you just take this difference, we measure it at 4,500, divide it by that, and it gives us Z.
The
one, that gives us 1 plus Z, I'm sorry.
So you, okay.
Yeah, that's great. Kyle and many others have spent a lot more time than I have looking at actual spectra to the point where they can actually by eye. In fact, I see some DESI members online are in the chat pointing out different features on the spectrum. So thank you. Okay, great. So we do the imaging first. And sort of on a related note, this is the point where I said that not all galaxies and not all photometry, not all spectra are built equally, right? So I've been very intentional with this galaxy that I've chosen for this nice illustration. Okay, beautiful spectrum, lots of features that we can talk about. Here's the extended galaxy. But you may recall Kyle mentioned we use different types of galaxies to probe different distances throughout the universe. So this is part of that bright galaxy survey. These are the big bright ones near us that we use to probe and study the recent nearby universe. But if we want to, extend this analysis to dark energy throughout cosmic history, we need to leverage those more distant, faint objects. So what I'm going to show you next are sort of the tricky galaxies that we use at larger distances. And when I show this, I really want you to notice how the spectrum and both the imaging change. Okay, are you ready? It's a very beautiful galaxy, very exciting here. Okay, so I'm having a little fun here, but much fainter. Okay, that's the thing I want to highlight here. So these are the most distant galaxies that we use to probe the universe. They're known as emission line galaxies or ELGs. Certainly from the imaging, you can see they're much fainter. They're generally bluer, more star-forming galaxies, and that's also reflected in the spectrum here. Now, if I zoom in a little bit on the spectrum so we can actually see some stuff, okay, the scale has changed here, but indeed there is some sort of slope to the spectrum. Okay, we have generally a little bit more blue than red light, hence the color. But effectively, the continuum is really hovering near 0. And it's really through this single emission line, and in this case, it's actually coming from oxygen, that allows us to determine its redshift and add them to this 3D map. So for the rest of this talk, I'm going to focus on these distant probes and really how this faint aspect of these targets can really add some nuance to the analysis. Okay, so once we have the 3 data points, now we can start calculating things like colors. And then we use those colors to determine which ones will actually get a fiber for spectroscopy. So this plot on the right is exactly what DESI uses to define targets for their ELGs. So I can calculate the difference between 2 of my data points. Here's G minus R. and on the x-axis is r minus z. And again, this gives me some intuition for the relative colors of these galaxies. And then DESI can draw a box here in black to define our target selection. So anything whose colors fall in those boxes will be targeted with a spectroscopic survey, and we'll get the redshift and do everything. I should say this box is, an informed decision. It's motivated by model predictions for how we best think we can describe galaxy evolution and galaxy formation. So it's really through these colors, through these broadband fluxes that we can identify targets. Now let's return to that faintness that I brought up earlier. So because these things are so faint, it can really alter how they fall into this box and how we select them. So first of all, you can imagine in these 3 integrated filters, the signal to noise may not be as ideal as we'd like. Okay, so there's a little bit of noise in these measurements, appreciable noise. And then also, you have to consider observing conditions when you calculate the fluxes through these filters. Things like dust from the Milky Way can alter the colors. If there's a lot of stars in that field, you may have trouble de-blending the stars from the galaxy. And so all of these are important characteristics that we need to consider when calculating these fluxes. And if we don't do so correctly, especially for these faint galaxies, we may bias our answer. So you can get things that may scatter in and out of the box. We may lose targets that we initially wanted. We may get unintended targets that scatter in and contaminate our sample. Or if we systematically don't calculate things correctly, we may overall shift the sample through this box and miss or preferentially grab certain parts on this color space. Okay, so that leads me to really talking about these observational properties. Okay, these are the things that we need to consider when estimating and calculating these integrated fluxes. So here are 6 different maps showing different observational properties or observational quantities. Within a given map, I'll point out a few things. First of all, you see the 2 patches. That's just the patch above and below the plane of the Milky Way. The white holes in the map are simply spots that DESI hadn't yet observed when this plot was made. But what's more interesting are the colored structures within each of these maps. So you can see the top left one, the extinction. Okay, again, this is tracing sort of the dust in the Milky Way, which can alter the colors. The stellar density I mentioned earlier. You can see as I get closer to the plane of the Milky Way, I get a more crowded field. Okay, so those are sort of intrinsic structures based on our own galaxy. We also have observational quantities, like the depth here. This is effectively how long we expose the camera or how faint we go in observing these galaxies. You can see there's clear structure here because we use different instruments for different parts of the sky. The PSF size, this is effectively how well we can resolve a point source given the imaging conditions. And so all of these things need to be considered, and because they have structure, if we don't consider them correctly, we may induce structure in our overall map of these targets. Okay? So that's exactly what you can see in this uncorrected map I have here, where this is the overall sky distribution or target density of these ELGs. We have overdensities in yellow, we have underdensities in blue, and many of these fluctuations are really just caused by the imaging conditions and structure themselves. Okay, you can imagine if I want to calculate the clustering as Kyle showed, this is certainly going to contaminate the measurement, right? So what DESI does is tries to work around this by running an independent model that should predict the structure given the observational maps, from which we can effectively take 1 over the model prediction and calculate some weights. So that's what you're seeing in this new map here. Now, if this is a perfect prediction, it would look effectively like the inverse of the original map, but there is it's not a perfect map, so there's some mismatch. But if we multiply these weights by our original map, you can see that we do a pretty good job of smoothing out a lot of that structure that was induced by the non-uniform imaging maps. Okay, so our ability to run a model and calculate these weights are a really critical part in DESI's pipeline. And so I'm going to talk and make some comparisons about those weights. Okay, so how do I derive these weights? Well, you can imagine sort of a first pass that we actually use for other types of galaxies is a linear regression, right? Where I pixelize the sky, I slice it into different patches. I count the number of galaxies in those patches and see how it evolves with the different imaging quantities. So that's what you're seeing on this right plot here. Up top, you can see how the target density varies with stellar density. Okay, for the ELGs in green, you can see that as I go to more crowded parts of the sky, I get a less dense target density. I can fit, a line effectively to that behavior and then back it out in an attempt to flatten this distribution, which is what you see in the bottom plot here. Okay, now of course, one major complaint is this always assumes some sort of linear relationship between the density and the properties. And I should note, you do this simultaneously. This is a multilinear regression. You do it on all different properties simultaneously. But again, you're restricted to only linear relationships. And so indeed, it gets rid of that, but you can see there is some residual, right? So there is motivation to go to a more free-form model. Okay, and so that's exactly what DESI does with these ELGs. It actually employs a neural network, which we call SysNet. Okay, so it passes to the neural network the counts of galaxies in each pixel. These are the labels. And then it passes as features the observational properties in those pixels. And then through several hidden layers, this machine learning, this neural network is going to have a much more freedom to derive some sort of relationship from which we can back out these trends that we see here. Yeah.
I mean, I'm surprised you went directly from linear to neural network. I mean, it doesn't make any sense to me. I mean, you've got so many nice little methods in between. I mean,
So I will say, I'm a lowly grad student, so I wasn't a part of this decision making. I don't know all the nuances.
Today is more, if you want to get funded, you probably want to do it neural network, but not
We can
for-
do it for funding. Well,
I could not imagine
Let me-
this kind of data. with a
let me
neural
say,
network.
part of the reason Tyler's doing what he's doing is I couldn't agree with you more.
Okay, thank you.
Okay.
Like,
That's right.
But anyway,
Yeah, there are many extensions of this linear regression, and you can build in quadratic relationships. So agreed. So a large part of this talk is going to be extending to sort of a compensation in between. Yeah.
It's like a kernel method is perfectly natural. If you really understand the bandwidth and all of that, you can, before going to.
we have a different thought, but well,
Yeah.
But like, why drive a Ford when you can drive a Ferrari, like. Because
So
a Ferrari will crash, you'll crash with a Ferrari more likely than out of your people.
yeah. So
I'm gonna die in a Ferrari crash.
So let me say a few words on this. So this is great, right? So why not just use the Ferrari? Why not use the open free-form model? When you do this analysis with such a free model, indeed you can capture non-linearities, but you also risk overfitting to the data. And specifically in this case, those maps that I showed you with the structure of the target density. Indeed, most of that is coming from the observational quantities, but there may be true cosmological information embedded in those maps as well. And so when we open the model to this more free-form idea, we're risking the fact of losing information on the actual cosmology. And then, if you're concerned about that and you want to investigate it, because it's nested in these hidden layers, you can't really look under the hood as easily as you would from a more analytical prescription.
Yeah, I mean, and the layer is doing really well, right? I mean, it's not like,
Yeah, so in fact, for some of the galaxy targets, it actually, we do use linear regression for some of the nearby ones. So in fact, that's what we're really going to explore. For the rest of these slides, we're going to return to the linear regression, but effectively introduce new free parameters. Okay, so you can see, even in this plot here, that the different types of galaxies respond differently to the regression, right? So that begs the question, can I go even further? Can I take my green ELGs, slice them up by property, and allow separate regression, separate treatment for these unique galaxies? The faint, the bright ones, the least and most massive, the blue and the red, relatively speaking, ELGs. So for the last few slides, we're really going to compare this neural network to what happens when we return to linear regression, but with new freedom with physically informed subsampling. Okay, so just to illustrate our method, that last box, we're going to start with all of our ELGs. We explore several different properties of interest. Here's just one. This is basically the flux coming from that emission line. It sort of traces star formation. Okay, and we split into subsamples according to this property. And then again, we perform the linear regression, but now allowed the freedom for separate treatment in different types of galaxies. How do the most star-forming ones, depend on the properties compared to the other subsamples? Okay, so we do this, and let's now compare the weights that we get out of this. Okay, so on the x-axis here on the right plot, I'm showing the original weights derived by the neural network on the whole thing together. On the y-axis are our new weights with linear regression, but split by subsample. Okay, if everything was in perfect agreement, we'd have great alignment with this black 1-to-1 dashed line. Indeed, on average, it all bounces around, but you can see there is variance, right? The mean solid lines, the average weights do vary, and they vary by property. Okay, oftentimes you'll see that our most extreme subsamples, our faintest and brightest in blue and brown, kind of have the largest fanning out, okay? And so we do see different weights, and we do see reason to have property dependence in this sort of analysis. So what does this mean on the clustering, which again, as Kyle said, is where we really extract information on cosmology and galaxy evolution and all these great things. So what I'm showing here is a comparison of the resultant clustering. Okay, this isn't exactly the same clustering statistic that Kyle showed, but it's not totally unrelated. So on the y-axis now is a ratio of two clustering measurements. First, it's our clustering measurement using our weights divided by the clustering using the nominal neural network weights. Okay, again, you'd expect if things are in agreement, they'd hover around the horizontal line of 1. But we do see some interesting features here, right? First of all, we see that there can be variations up to 10% on average. We see a global shape where things trend downward. So this is telling us that the slope is actually steepening in the clustering when you use our weights. And once again, it's the extreme samples, the faintest and brightest, that have the largest difference, okay, up to a factor of 2 in some of the extreme bins. And so you can imagine if I want to extract information not from the BAO, but from the broadband slope of this clustering, I really should consider property dependence if I'm going to do some sort of galaxy evolution analysis. So we think there's motivation here to do this sort of subsampling weighting scheme. You may recall, however, that in Kyle's plots, DESI, its overall mission does not split by galaxy property, right? We're going to treat all ELGs as a single distant tracer. So that makes us wonder, okay, how do our weights compare to the original weights for the overall global clustering of all ELGs? So that's the last plot I'm going to show you. Again, just to be clear, we start with all ELGs, we split into the subsamples. We do linear regression to calculate their property-dependent weights. And now we're going to basically squish them all back together into one sample and compare it to the original DESI measurement. So that's the last plot I'm going to show you here. Pretty consistent. Okay, so again, clustering statistic on the vertical axis. In blue here are the clustering with the original weights, and orange here is the clustering with our property-dependent, maybe simpler linear regression weights. You can see a lot of consistency, so I think that's great. I think that tells you a few things. One is that it's telling you that the neural network is really picking up mostly linearities in our property dependent, or in our imaging maps. And number two, I think it's telling us that we do have the choice, if we want to look more under the hood, to switch to this linear regression based on subsamples and really investigate what's going on. So I think consistency is great. We were sort of hoping to maybe see a big change and maybe a discovery here. But I will finally say, you can see a trend on large scales where there is a little bit of difference. Maybe if I go to larger scales, I'll also see that. So it's a little bit speculative. But if that trend continues, it's at least in a direction we might expect, where with our new weights, we're recovering true cosmological or galaxy evolution information that's otherwise overfitted and removed by the neural network. Okay, so I think there's interesting things that we can really get out of this work.
Sorry for statistical geeks. How are you computing the error bars on this thing?
This is a jackknife procedure. Yeah. So you slice up the sky into over 100 different subsamples. Yeah, no, it's a great question. Yeah. Okay. So that's the last I have. So I really want to just summarize with a few key points. Okay. Number one, I think is the most exciting for this audience. DESI has to correct for these imaging systematics, right? And it actually employs a neural network to do so. So this is a direct evidence of the synergy between machine learning and astronomy. And it's being done on what I think is the most exciting galaxy spectroscopic survey ever done with hints of new physics. So I think that's really great. Number two, if you're going to split your galaxies into some sort of unique property, okay, you may want to build in the property dependence, as I've shown. It has real consequences. And number three, sort of that last plot I showed, both weighting schemes seem to seem to achieve the same result for the overall DESI mission. And perhaps there are hints on large scales where we could get some interesting results. So the last thing I'll say is, one final step is you could actually fit, your cosmological model to these different weighting procedures to the clustering. And so we could actually explore, other consequences and how we constrain dark energy and the other cosmological parameters using these new weights. The collaboration and myself aren't quite ready to do so. So stay tuned. That'll be an interesting thing. And we can see how these seemingly small choices can really affect how we understand dark energy and our universe as a whole. Okay, thanks.
Great, so we can take some questions in the room or online. They're starting with one online from Stephanie. So Stephanie, if you're there, you can unmute and ask it.
Yes, I'm still here. Nice talk, Tyler. I guess, can you go back to your slide where you were comparing in bins of luminosities?
Yes.
I think I missed a little bit.
Here, maybe?
No, the other one, I think just before.
Here.
Sorry, maybe was it after? You were, I think it was showing a bigger deviation at low and high luminosity and less deviation. Yes.
Yes.
Yeah, so I'm not sure if I follow here because, naively, I might have thought, okay, maybe there's going to be some kind of trend that's monotonic with luminosity, but it doesn't seem like that. So are there like different reasons? Like I'm surprised to see the lowest and highest, or
yeah. So
yeah.
we're thinking about this lack of a monotonic relationship. If instead of plotting the ratio, if I were just to plot the clustering, you would see that the clustering starts off high and then low and then back up high. In terms of the new weights, I think that the reason that the two most extreme bins are experiencing the largest change, though, is because they're the furthest from the average galaxy in the sample, right? So you can imagine if I do linear regression on everything together, I'm hand wavy here, effectively regressing on the average ELJ sample. And so because the outliers on the outer tails of the distribution should shift the largest. I think that's maybe the intuition here.
You could imagine that the ones that are furthest from average are the ones most susceptible to systematic errors.
Yes.
So they're the ones that produce the most spurious signal when they're not corrected for properly.
Yes, I don't know if you could hear that, but Kyle had added.
Yeah, I did. Yeah, we heard it online. Yeah, I guess that makes sense. I feel like this should be still two different reasons why they go in the same direction. Like the biases we have when we observe at the bright end and the faint end, the luminosity functions are two very different. Anyway, okay, thanks.
Yeah, thanks. I agree. It's a thing that we should still consider, and I think there are physical reasons to expect why the bias would maybe do this V shape, but with luminosity. But yeah, we'll keep looking.
Thanks.
There's another question from Brian online. Brian, can you unmute and ask? No, I can read it.
Can you hear me?
Yes.
Sometimes that works. Yeah, thanks. Thanks for the nice talks. I had thought I'd understood that the imaging, the systematic corrections that were being done by SysNet fit into the overall kind of a data reduction and observing pipeline as a correction before the target selection for spectroscopy. Is that correct? And if it is correct, how do you measure clustering both ways? I think I must be misunderstanding where it fits in.
No, I don't think that the SysNet derivation is embedded into the target selection. It's only applied after the fact to the spectroscopic samples.
And so it's used to classify targets into different subgroups. How does it fit in? I'm missing something.
So what are you referring to when you say it?
SysNet.
The
whole.
I see. No.
The correction you're doing.
The neural network SysNet. It's not used to classify galaxies at all. It's purely to correct the clustering in the final measurement. The galaxy types are classified with a different algorithm called RedRock that we use to get the redshifts effectively.
But one of the bottom lines is that we can't apply these corrections until after we have the sample of galaxies with proper redshift. So we actually know what to correct in terms of number density. We don't have a number density until we have the spectroscopy. So it can't be done until after the whole target selection is complete. We look at it to get idea of the dangers of it in the target selection process, but we can't actually do this properly until we have the redshifts.
Great.
Okay,
Howard?
thanks.
Yeah, thanks.
So maybe we'll stop here, and thanks to Tyler and Kyle again. So thank you.
Thanks, everyone.